In section 9.1, we're going to learn about the Pythagorean theorem and all the different ways in which we can use it. So first thing is just identifying and discussing what exactly is the Pythagorean theorem. First of all, the Pythagorean theorem only works for a right triangle. Okay, so when you happen to have a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. Now, we call the legs sides A and side B, and we call the hypotenuse side C. So in a right triangle, the two sides that form the right triangle, A and B, they create that right angle. Those are your legs, and the side opposite is your hypotenuse. An interesting fact is that your hypotenuse is the longest side of the triangle. And so the formula for this, again, we write it out, is a squared plus b squared equals c squared. And so, again, the legs squared, the sum of the legs squared equals the hypotenuse squared. So if I happen to have a right triangle here, and I tell you that this leg is 4 and this leg is 5, and I ask you to identify the hypotenuse, you're going to do 4 squared plus 5 squared equals the hypotenuse squared. 16 plus 25 is the hypotenuse squared. We're going to do 41 equals c squared. And since I'm looking for c, I take the square root of both sides, and I'm like, oh, c is the square root of 41. And that's a simplified radical, and you're done with that. It doesn't matter which side I give you. I might give you, maybe I give you a side and the hypotenuse, a leg and the hypotenuse, and I ask you for the other side. So again, you're going to tell me then that it's a squared plus b squared equals c squared. So 9 plus b squared is 25. B squared is 16, and when I take the square root of both sides, I get that b equals 4. So I can use the Pythagorean theorem to identify the hypotenuse or to identify a missing leg. What I just have to remember is which one is the hypotenuse. A and B can be switched up, but C cannot. When we use the Pythagorean theorem, we're going to get some common triples. And first of all, what makes a Pythagorean triple? Well, a Pythagorean triple exists when every value, all three sides, are integers, okay? Or whole numbers, okay? If you want to refer to it that way. Let's say whole numbers, that's probably better. In other words, the sides are not fractions or decimals or anything like that. They are whole numbers. And when you memorize them, it's actually kind of helpful. For example, in that last example, I knew that the side was 3 and the hypotenuse was 5. Well, if I remember these triples, I know that one leg is 3, one leg is 4, and the other leg is 5. If I don't memorize them, it's not a big deal because I can do the Pythagorean theorem and find the missing piece like I did in the last problem. However, if I can memorize these common triples, it's helpful. Not only is 3, 4, 5 a common triple, but all their multiples are as well. So for example, notice this one. 3 times 2 is 6, 4 times 2 is 8, and guess what? 5 times 2 is 10. So if I follow that pattern, then if you get a triangle that you know is like, let's say 9 and 12, you're like, wait, 3 times 3 is 9, 4 times 3 is 12. That means this third side is 5 times 12 or 15. So again, if you can kind of get good at recognizing the basic ones, then you know all their multiples are as well. They're not all related to 3, 4, 5. Sometimes you get 5, 12, and 13. So again, let's just pretend we didn't know that the hypotenuse here was 13. We could figure this out mathematically because we know 5 squared plus 12 squared equals c squared. 25 plus 144 equals c squared. 169 equals c squared. And when I take the square roots, I get 13. So I'm able to mathematically solve for it. But again, it makes it a lot easier if I can memorize these. You do want to memorize your square roots of, basically you want to know all the numbers squared through 15, you want to know all the square roots, of all those. So 15, 15 times 15 is 225. You want to know the square root of 225 is 15, and vice versa. So now let's actually apply the Pythagorean theorem from obviously more simple problems to more complex. Again, you want to identify your legs and your hypotenuse. So it's important to always know where your hypotenuse is, right? Because that hypotenuse is always going to be your C value when you're thinking of A squared plus B squared equals C squared. So for A, let's work this one out. We've got our legs are 5 and 10. So 5 squared plus 10 squared equals C squared. 25 plus 100 equals C squared. 125 equals C squared. And so I know that C equals the square root of 125. Now here's where you have to remember how to simplify a radical. I know that 125 is 25 times 5, and I know that 25 has a square root of 5. So 5 radical 5 is the simplified radical answer here. If I use my calculator, then I would get some type of decimal or whatever. But we won't be using calculators on these types of assessments, so you're going to have to simplify the radical. When we go to B, let me do B in a different color. So here again, I've got a little bit more interesting problem here, right? I've got 5 squared is one leg. The other leg is y minus 1 squared, and it equals C, which is y squared. And so I have to FOIL this. This is going to be 25 plus y minus 1 times y minus 1. So let's get to FOILing that, right? That's y squared minus 2y plus 1 equals y squared. Again, I'm going to combine my like terms on the left side, and I get plus 26 equals y squared. And because I have a y squared on both sides, I know I could subtract it out. So I'm going to get negative 2y plus 26 equals 0. I'm going to move the 26 to the other side by subtracting it. And then I'm going to divide everything by negative 2, and I'm going to get y equals 13. So again, in this problem here, it's 13. And notice this is a Pythagorean triple, 5, 12, and 13. And then the last one I'm going to do has some kind of interesting numbers here, right? I'm going to do, again, leg squared plus the other leg squared equals the hypotenuse squared. So x squared plus 9 equals, now 3 radical 2 times 3 radical 2. Remember, when you're dealing with radicals, you're going to multiply the outside numbers. 3 times 3 is 9. And you multiply the inside number. 2 times 2 is 4. And so what you get is 9 times the square root of 4, which is 2. So x squared plus 9 equals 18. And if I subtract 9 from both sides, I get x squared equals 9, which means x is 3. So x is 3 here. And so now I've been able to solve all of these problems using the Pythagorean theorem. So now we're going to come and try to solve some additional problems they're going to give you. So just read the problems carefully. It says the length of a diagonal of a rectangle. So first let me draw the rectangle. I've got the length is 8, the width is 4, and I know that the diagonal of a rectangle goes from one corner to the other. That's a terrible drawing, but notice I have this right triangle here now, right? I've got my legs, 4 and 8, and I'm looking for the diagonal, which notice it's the same as my hypotenuse. So now I know that this is 4 squared plus 8 squared equals c squared. I've got 16 plus 64 equals c squared. 80 equals c squared. So I know that the hypotenuse is the square root of 80. Now again, I have to, at this point, try to figure out, right, how can I simplify this as best as possible? Well, I know that 80 is the product of 16 times 5, and I know that 16 has a square root of 4. So 4 radical 5 is the simplified version of square root of 80. And again, that's kind of how we solve it using simplified radicals. Again, we come to the next one, and it says the diagonals of a rhombus have lengths 16 and 30. Find the perimeter of the rhombus. Now that's kind of interesting. So here's a rhombus, right? Remember that rhombuses have all four sides are equal. So I know that this side has to equal this side, which equals this one, which equals that one. So I also know that the diagonals of a rhombus intersect at 90 degrees, okay? And they also split each other there in half. So what happens is if my rhombus has lengths of 16 and 30, then I know, for example, this is 8 and this is 8, and this would be 15 and this would be whoops, not that. This would be 15 and 15, okay? So I've got the one diagonal, the long one is 30, the shorter one is 16. They completely bisect each other, and what really is of interest is notice that they form right triangles. So I basically have three more in addition to this one, so 4 right triangles, and all the right triangles have the exact same measurements. They have 8 and 15, and notice that the hypotenuse is one of the sides of the rhombus. So if I can just figure out what the hypotenuse is, I know what each side of the rhombus is, which then helps me find the perimeter. So again, I've got leg squared plus leg squared equals hypotenuse squared. I've got 64 plus 225 is c squared. When I do the math here, I get 289 equals c squared. And I know then that c is the square root of 289. Now, some of you guys at this point might be scrambling, trying to figure out what number has a square root of, or what is the square root of 289? Well, it ends up being 17. C equals 17. And again, if you go back to your Pythagorean triples, you're going to see that 8, 15, and 17 is one of the common ones. But we figured it out mathematically. C is 17, so if the side of the rhombus is 17, all the sides of the rhombus is 17. So the perimeter is 17 plus 17 plus 17 plus 17, or 4 times 17, right? Which is going to be 68. So the perimeter is 68 units long. In this problem, I'm going to apply some skills I've learned before. I know that if the legs of this triangle, or these two legs, right, basically from here to here and here to here, I know if these two are congruent and there's this line that meets at a right angle down here, I know that not only does it bisect this angle into 2 equal pieces, it also bisects the side into 2 equal pieces. And so I know that if the whole side is this 6, I know that this is 3 and this is 3. And so again, once I do that, I realize that I've got the legs of a right triangle. I've got one leg is 3, one leg is 6, and I'm going to use the Pythagorean theorem to find the c, which in this case is x. So I've got 9 plus 36, 9 plus 36 is x squared. 45 equals x squared, and I take the square root of each side. So the square root of 45, which again needs to be simplified. I know 45 is 9 times 5, and I know that the square root of 9 is 3. So 3 radical 5 is the length of x. So now we have some converses here of the Pythagorean theorem, right? And what it basically, remember the converse is just flipped over. So remember that we know that if a triangle is a right triangle, then the a squared plus b squared equals c squared. Here we're working it backwards. Here we're saying that if c squared equals a squared plus b squared, then it is a right triangle. So if we're given that a squared plus b squared equals c squared, if we figure that out, then we know the triangle is a right triangle. We also know to have these inequality theorems which help us to understand that if a squared plus b squared is not equal to c, if a squared plus b squared is not equal to c squared, then we know that we can determine what kind of triangle it is. okay? So there's a formula. If c squared happens to be less than the sum of the other two sides squared, then the triangle is an acute triangle. And if c squared is greater than a squared plus b squared, then the triangle is an obtuse triangle. And again, we can use these inequalities to tell whether a triangle is right, and if it's not right, we can tell you what kind of triangle it is. So here we come to these problems, and it says the sides of the triangles have the lengths given. Is the triangle acute, right, or obtuse? Well, first of all, you want to identify what would potentially be, or what is your C. Remember, C, we're going to make it always our longest side. And in this problem, they gave them to you in order. They don't always do that on problems, so you always have to kind of scan through and identify the longest side. That's going to be your C. So in A, you've got c squared, and then you've got a squared plus b squared. And we're going to try to figure out the relationship. We've got 29 squared, 20 squared, plus 21 squared. So we have 841, 400, and 441, and I get 841 and 841. Well, I know that this equals it. So in this case, this is a right triangle because c squared was equal to a squared plus b squared. I'm going to keep going. I'm going to do the second one. So B. So in B, again, I've got the largest side, 30 squared, and then I've got a squared plus b squared. So here I have 900. Here I have 400 plus 441. 900, I have 841, and I notice that 900 is greater than 841. Well, that means that my triangle is obtuse because c squared was greater than a squared plus b squared. In C, I come over here and I do 8 squared, 5 squared plus 6 squared. I get 64, 25, and 36. 64. And I have, that's 56, 61. And 64 is greater than 61, which means this is, again, an obtuse triangle here. So I'll come over to D, and I say, all right, I've got 8 squared, 4 squared, plus 4 radical 3 squared. So I got 64, 16, and 4 radical 3 squared is 16 times 3, which is 48. So 64, 64, so that's equal. And so that ends up being a right triangle again. And then the last one, E. And I've got square root of 10 squared, 1 squared plus 3 squared. And so this is 10. This is 1 plus 9, so 10 and 10, they're equal, which means it's a right triangle. And that's how we do the math and solve this and figure out what the triangles are. So methods for classifying a triangle by angles using its side lengths. So again, how do we classify a triangle as acute, obtuse, or right? We use this method here. We use this formula. If c squared equals a squared plus b squared, then it is a right triangle. If c squared is less than a squared plus b squared, it is an acute triangle. And if c squared is greater than a squared plus b squared, it is an obtuse triangle.